So I'm going to be talking about full stack development with the Grand Stack, which is GraphQL, React, Apollo, and Neo4j database. So my name's Will. I work at Neo4j, which is an open source graph database. I don't work on the core engineering team for Neo4j. Instead, the team I work on builds integrations. So making sure that you can use Neo4j with your favorite web development framework, that you can move data back and forth from different data processing frameworks, tools like that. And so what I'm going to talk about today is largely the most recent integration that I've been working on, which is a Neo4j GraphQL integration, which makes up a big part of the Grand Stack. But if you get bored while I'm talking, you can go to bit.ly/graphhacker, and there's a little challenge there. Basically, it will take you to an Apollo Launchpad, which is a tool for building a GraphQL service in the browser. And there's just a couple of steps to follow. Basically, just connect that Launchpad to a hosted Neo4j instance and get the GraphQL service working, and then just tweet us about it, and we'll send you one of these cool Neo4j GraphQL hacker t-shirts. And you don't have to do it while I'm talking. You can do it later too. Cool. So what do I want to talk about? Well, I want to talk about this idea of the Grand Stack. So these technologies that we can use together to build full stack applications. Because most of us are developers, I want to talk about focus on the how we do this. So we're going to go through some code samples of how we can build a full stack Grand Stack application. But first of all, what is the Grand Stack? What are these components? So the first component of the Grand Stack is GraphQL. How many people have used GraphQL at all? Okay, cool. So that's maybe like I'll call that like 2/3 of the audience. So GraphQL is this new paradigm for building APIs. It's an alternative for building REST APIs. It's very focused around a schema definition. So we start by defining a schema. We define the types that are available, the fields available on these types. And then we can select from this schema on the client which fields we want in our query. The other component, or say the next component, is React. How many people use React? Okay, that's a lot of folks. Cool. So as you all know, React is this JavaScript library for building user interfaces for web, native, VR. Very much focused on components that encapsulate data and logic. And then we have Apollo. How many people have used any of the Apollo tooling? A few folks, yeah. So Apollo is not just a single tool. Apollo is instead a suite of tools for working with GraphQL. So you see Apollo show up both on the client side with things like Apollo Client, and then also on server-side tooling for building a GraphQL service, things like performance monitoring and mocking. So when we say Apollo, in this example today, we're going to look at the Apollo client, specifically the React integration for Apollo client. But really, there are lots of different Apollo projects that help with working with GraphQL throughout the stack. And then the final component is Neo4j database. How many people have used Neo4j? Okay, a few. So Neo4j is a native graph database. What that means is that we use the property graph to store, model, and query data as a graph. So nodes are the entities in the graph. Relationships connect them. We can store arbitrary key value pair properties on nodes and relationships. We use the Cypher query language for working with data in Neo4j. You can see an example at the bottom of the screen there. And then we have client drivers in lots of different languages for working with Neo4j. So in the example today, we'll be using the JavaScript driver for Neo4j. Cool. So those are the individual components of the grand stack. How do they fit together? Well, let's look at a simple example. Let's consider a super simple movie search and recommendation web app. So what are the requirements for this? Well, a user should be able to search by title and then view some movie details for any matching movies. And then we also want to show personalized recommendations. So for this movie that a user searched for, what are some other movies that the user might like? And if you're familiar with graph databases, this kind of recommendation query is really easy to express in a graph. So if you use Amazon or e-commerce things, people who bought this also bought this. For movies, someone who viewed and rated this movie highly also rated these other movies highly. That's a simple example. We can do much more complex things, but that's the general idea. Okay, so with that sort of that application in mind, how do the pieces of the grand stack fit together? Well, we have React on the front end. The user types in their movie, River runs through it, hits search, and the Apollo client integration, in this case, sends a GraphQL query to our GraphQL service. Our GraphQL server has logic in there to query our Neo4j database to look up movies by title, and that data comes back to Apollo client. The React integration for Apollo client binds the GraphQL query result to the props for our view, for our component, and the view is rendered. Okay, so that's how those pieces fit together. Let's look at that in a bit more detail, starting at the data layer. So starting with Neo4j. So since not everyone is familiar with Neo4j, I want to spend just a little bit of time talking about what is Neo4j. And I think the best way to explain something is often in the form of a tweet. So here's Neo4j in 140 characters. I guess I could redo this in 280 now. But. So Neo4j is open source software that stores and queries data as nodes and relationships using the Cypher query language with index-free adjacency. Okay, so there's a bit going on there. Let's dissect that a bit. So first of all, Neo4j is open source software. All the code is on GitHub. We can go build it from source. We can download it. We can use the Docker image for Neo4j. So lots of different ways to get Neo4j. Neo4j is primarily a database, so focused on modeling, storing, and querying data. So when we write some data to Neo4j, it's durably committed to disk. Neo4j is not just an in-memory processing framework. It's very much a database. Okay, so it allows us to store and query data as nodes and relationships. So we said that nodes, these are the entities or the objects in the graph, and relationships connect them. So relationships are first-class citizens in the data model. And we can store key value pairs, so properties, attributes, both on nodes and relationships. And if you look at this data model, this might look somewhat familiar if you've been following the news recently. So this is the data model from the Paradise Papers data leak. So this was leaked data from, in this case, a law firm in the Bahamas that had lots of information on rich people that had connections to offshore legal entities. And the data journalists that were working with this leaked data, they use Neo4j to make sense of the connections to these offshore legal entities. And this makes sense if you think of a person who has some shareholder interest in a legal entity that is the beneficiary of another legal entity that is a shareholder in an offshore trust and things like this, where there's a very long path to get to the ultimate beneficial owner. So that kind of data makes a lot of sense to work with in a graph. So we model, store, and query the data as nodes and relationships using the Cypher query language. So here's a Cypher example. And this again, this is querying the Paradise Papers data set. So this is saying find addresses in London, find all of the officers, so in this case the people, find all of the people with addresses in London, and then for those people find all of the legal entities that they're connected to. So you can see that Cypher is very much about pattern matching. In that first line in the match statement, we're defining a graph pattern. So we define nodes within parentheses, relationships within brackets, and we're basically traversing the graph to find paths that match this pattern of people with addresses in London and their connections to offshore entities. And if we run this in Neo4j browser, we get this graph visualization. Okay, so these are all of the people with addresses in London that have connections to offshore legal entities from the Paradise Papers. And this is useful to sort of see where there are some highly connected clusters. We can see a couple of connected clusters there. There's something interesting going on there, someone that has lots of connections to legal entities. Okay, that's interesting. But oftentimes, the answer to our question is not a graph visualization. Maybe it's the result of an aggregation, or maybe it's tabular data. So we can modify our query slightly to ask a different question. In this case, we're saying, okay, for all these people with addresses in London that have some connection to offshore legal entities, what are the most common jurisdictions for those offshore legal entities? So for people in London, where do they like to hide their money offshore? Well, Bermuda is the most common offshore jurisdiction, followed by the Cayman Islands. Mauritius is on the list as well. So the point there is just that graph queries are not just about graph visualizations. We can do sort of the same things that you would expect from other query languages like SQL and that kind of thing. Cypher is part of the OpenCypher project, so it's an open query language that is implemented by other databases, other processing frameworks. We can use Cypher with Spark, for example. Okay, so back to our tweet. So Neo4j open source software stores and queries data as nodes and relationships using Cypher with index-free adjacency. So this last part, index-free adjacency, is an important performance characteristic of graph databases. What this means is that when we traverse from one node to any other through a relationship that we're connected to, we're not doing an index lookup. That means that the performance then of a local graph traversal is a constant time operation. It's not dependent on the overall size of the data. So our query is on a data set of a few million nodes, then can scale to one with several billion nodes. So we can scale these queries to very, very large data sets. This is a really important performance characteristic of graph databases that's very different from other types of databases. Okay, so that was my Neo4j in 140 characters overview. If you're interested in playing around with Neo4j or that Paradise Papers data set as well, Neo4j Sandbox is a good example of a way to spin up Neo4j instance with some different data sets. They're hosted on AWS with some example queries you can play around and get started. Okay, so let's take a look at some data in Neo4j, since we said we want to build out our movie recommendation app. And I said we were going to look at data about movies and user ratings, but I lied. Instead, let's look at some data about Russian Twitter trolls. So again, if you've been following the news, at least this has been big in the US, I think in Europe too, but there's been investigation into Russia's meddling with the US election, especially through social media. And so Twitter released a list of 3,000 screen names that are tied to Russia, and then promptly suspended those accounts, which deleted all of the tweets from twitter.com and from the Twitter API. So we can't really figure out what those 3,000 Russian trolls were tweeting about. But I found some of them on Internet Archive. So I scraped Internet Archive for all the tweets I could find by these Russian trolls and put them in Neo4j. So here's the schema that we have. So we have a tweet. A tweet was posted by a user. So user posted a tweet. Then we have hashtags. We have URLs that the tweet might contain. And then I also ran some simple natural language processing, like entity extraction, to find any people, organization, or locations that any of these tweets mention. So let's look at an example query. So for one user, this is 10_GOP. So this was an account that was intended to look like a political party of the state of Tennessee in the US, but was very much not. So we can say, okay, show me all of the tweets posted by this user and that have a hashtag, and show me all of the hashtags for these tweets. And we can get back sort of this sort of visualization. So here's the user. It's posted some tweets. So here's something about civil rights that Trump is taking away. We can see some of the hashtags that are used. We can see here that here's several tweets from this user that use the hashtag Barcelona, so we can sort of get an idea of what this account was tweeting about. And we can run queries over the full data set. So this one is interesting. What are the most common hashtags that are used? And for some reason, there is a lot of tweets that we captured in German, targeting, I think, things going around Merkel's re-election in Germany. We can also look at the hashtags used together most frequently, which I think is also interesting. And again, we get a lot of German tweets there. Okay, so that's the data set that I actually want to work with instead of movies. So keep that data set in mind, and we'll talk about how to build a GraphQL service on top of this. So first of all, let's talk a little bit about GraphQL. So we said that GraphQL is this new paradigm for building APIs. It's not really a query language for a database necessarily, but instead it's a query language for APIs. So it's a way of specifying data and then querying the data, but limited support for what we would think of as queries. So like there's no support for aggregations or filtering, things like that. And then there's also a big community of tools built around GraphQL. So Graphical, which we'll look at in a second, is this sort of in-browser IDE for working with GraphQL. We already mentioned mocking and performance. So the schema is really important in GraphQL. It defines what data is available, and then a client, for any given request, selects only the data that the client is interested in from the schema. And this reduces then the amount of data that's sent over the wire, and it also allows the client to pick the data it needs to render a particular view. And these were the two reasons that Facebook created GraphQL originally, was to be able to render a view with a single round-trip request and to reduce the data sent over the wire. So this was particular to Facebook's native apps over slow networks, where this sort of network latency is really obvious when you have multiple requests to render a view. GraphQL also makes this observation that your application data is a graph, and we'll come back to this in a minute because I think this is pretty important. So here's a GraphQL query. We're looking up a business by ID, and then we're specifying some fields that we want to grab. Okay, so what's the graph piece of this? Well, GraphQL makes this observation that your application data is a graph, sort of irrespective of how we store that on the back end. But when we're talking about our application data in the client, that's a graph, and we're traversing it with GraphQL. So we're starting from the business. We're then seeing, okay, what are the categories connected to this business? Okay, for those category objects, what are the name property associated with that, and so on. So we're traversing this graph. And we get back our results. Notice that the shape of our result matches our query, because those are the fields that we specified that we're interested in. So this observation that your application data is a graph is interesting because it implies then that if you're not using a graph database on the back end, if we're using a relational database or a document database, then there's some sort of mapping and translation that has to occur from our application data graph, GraphQL, to how we're storing and modeling that data in the back end. Let's take a look at graphical so we can sort of see our data being queried live. So here's graphical. This is sort of this in-browser IDE for working with GraphQL. And this is querying the Neo4j database that I have running. So let's just grab the first 3 tweets. So we're querying for hashtag politics, finding the first 3 tweets, grabbing the text, but we can also see all of the other hashtags in the tweet and so on. So you can see how our response is changing as we're adding more fields here. Skip some of these slides and talk about how we build a GraphQL service. So, so the first thing we do is define a schema, and then we define resolver functions that define how we fetch data for that schema. Here's our movie schema, but let's take a look at our Russian Twitter troll schema. Looks like this. So we have, it's pretty simple. We have 3 types. We have a tweet, we have a user, we have a hashtag, and we also have a link. And you can see the fields that are available. So a tweet has a text, it has a permalink, and our fields can reference other types. So a tweet has an author, that's a user here. And then the other important thing that we define in our GraphQL schema is the entry point for our GraphQL service. So here we have 2 entry points. So these are the queries, the GraphQL queries that we can run. We can start by looking up hashtags by tag, or we can do tweets by text. So search the text of tweets to find tweets. And we define our schema using the schema definition language, which is this sort of language agnostic way of defining a schema. Okay, and then we said our resolver function has the logic for fetching that data. So this is what a typical resolver function looks like, where for our entry point, we define how, in this case, a Cypher query to look up a movie by title. But then we have some other fields that's not resolving, so things like our recommended movies. So we have to have another query to find our recommended movies. Our genres are in another node, so we need to have another query to find our genres. So if we end up with a non-trivial GraphQL query, what we end up with are lots of these different queries that are multiple round trips to the database. So we end up having to batch these for performance. And this is typical for really any GraphQL implementation. So what we wanted to look at was, well, could we build a Neo4j GraphQL integration that offers some developer productivity benefits, right? Like implementing those resolvers seems kind of tedious. We're just sort of writing Cypher queries there, and if we do this with a relational database, we're writing SQL or we're writing our ORM queries. So is there a way that we could translate GraphQL to Cypher and then not have to write those resolver functions? And then would this give us better performance because we can just generate a single Cypher query, so that's one round trip to the database rather than having to batch a bunch of queries. And then could we expose Cypher through GraphQL? Because we said GraphQL is somewhat limited in support for projections, aggregations. So these are the things we wanted to explore. And so we built what we call Neo4j GraphQL JS, which is a integration for GraphQL and Neo4j that basically takes the GraphQL schema and uses this to drive what the Neo4j data model should be, which then allows us to translate arbitrary Cypher queries to, arbitrary GraphQL queries to Cypher. And what this means is that for any given GraphQL query, there's just a single Cypher query, so a single round trip to the database. And Neo4j has a very smart Cypher execution engine, so those end up being optimized pretty well. And then we can also expose Cypher in GraphQL with a Cypher directive. So in our schema definition, we can annotate any of these fields. So this is a field called similar on our movie type. So we said we needed to generate movie recommendations for a movie. So this field similar, in this case, we're just looking for movies that have the same genre. But we could have a much more complex query there looking at user ratings or something like that. And that then becomes a computed field. So that's this idea of the Cypher schema directive. And that still is just one Cypher query that we are able to generate. That computed field essentially becomes a subquery in our Cypher query. Okay, so we thought that was pretty good. And if we take a look here, this is the GraphQL Server implementation that I was hitting when I was running GraphQL here, so my Russian Twitter data. And this is the only code to implement my resolver. So I don't have to write any Cypher there. Basically, all I'm doing is calling the Neo4j GraphQL integration, passing along the GraphQL query and any parameters. And our integration is generating the Cypher behind the scenes. These are the generated queries. So here you can see we were looking for the hashtag politics and looking for any tweets that have that hashtag and so on. So anyway, so I think that this was really cool. This was a big, I think, developer productivity boost. It allows you also still to have the flexibility of querying other services. So if you want to fetch data from another database, you can do that as well. Just implement your own resolver rather than calling out to the integration. Cool. So that's the Neo4j GraphQL integration. I'm about out of time, so I'm gonna skip over this React piece. I think we're all pretty familiar with React. The only thing I want to say about the React Apollo integration is that Apollo client, the React integration for Apollo client, is really neat because it allows us to basically bind a component's props to a GraphQL query. That's sort of the only missing piece here. And my super simple React app that I wrote in just a few minutes, as you can see, with no styling or anything, basically just allows us to search by hashtag. So all it's doing is binding our tweet list props to a GraphQL query. Anyway, the code is online if anyone wants to check that out. I just want to mention a couple of things. One is that these sorts of integrations that we're building, these are largely feedback driven. So if this sounds like an interesting project, like something that you might want to play around with, please do, and then let us know what you think. Are there features that would be helpful? Let us know. We can build them. Because really our goal is to sort of figure out what sort of integrations like this make sense to make it easier to build cool applications. So I'll mention just a couple of resources. The Neo4j sandbox, which I mentioned before, is a great way to get started with Neo4j. It has this data set for movies and movie recommendations that power the movie app that I didn't really talk about, but has other data sets as well that are really fun. And this portal, grandstack.io, this is sort of a landing page that collects lots of information about these integrations that we're working on, has documentation and tutorials for these different projects. So if you want to get started looking at GrandStack apps or any of these integrations that I talked about, that's a good place to start. Cool. So that is what I have to say. Yeah, question. Yeah. So the question is, there's this other database called dgraph. Why would I use Neo instead of dgraph for a GraphQL integration? So dgraph is a triple store. It's not quite the same thing as a graph database, but for intents and purposes, it's very similar. They use something kind of like GraphQL for their query language. They call it GraphQL plus minus, I think. So they sort of have added some things to their flavor of GraphQL, and like they've added some filtering functions and things like this. And the problem with that is because it's not GraphQL, it means that that doesn't work with any of the other GraphQL tools. So you can't just like wire up Apollo client to it because it's not GraphQL, so things will break. There's actually, I won't bring it up here, but there's a really good GitHub issue where some of the Apollo folks basically said, hey, you say this is GraphQL, but it doesn't work with any of our tooling. So what's going on? So anyway, so that's one thing that I think is a bit confusing about dgraph, is it's not actually GraphQL that is compliant with the spec that works with other GraphQL tooling in the ecosystem. But having said that, what they've done with the GraphQL language is really interesting because they've taken an interesting query language and sort of added missing functionality. I just don't think they've done it in a way that plays well with other tooling. So anyway, the answer to your question is sort of if I want to build a GraphQL app with Neo4j or dgraph, an important consideration is how does it work with other tooling in the ecosystem. And so these Cypher schema directives, these are sort of the built-in way in the GraphQL spec to sort of extend GraphQL. So this means that we're sort of extending GraphQL by annotating these fields, but we're doing it in a way that is compliant with the spec, and that means that it'll work with all of the other GraphQL tooling in the ecosystem. Well, thank you. If there's no more questions.